The design strength of a member under axial tension is lower of the design strength due to yielding of a cross section TDG, rupture strength of critical section TDN, and block shear TDB. We have seen that the tension member undergoes three kind of failure, that is yielding of a cross section, rupture at a critical section, then block shear. The tension members undergo three types of failure. That is why we need to calculate the strength in all the three criteria. Whichever is the least, that is the strength of the tension member under axial tension, that is TD. Now let's look one by one. First is the design strength due to yielding, high deformation of a cross section. And if you look IS 800 class 6.2, where it has been given that TDG, tension strength in a gross yielding, is equal to AGFY upon partial safety factor. As we have already discussed the partial safety factor, it is given in the table number 5. Gamma M naught, resistance governing by yielding, gamma M naught is 1.1. And if you look the equation, area into yield stress upon partial safety factor. Okay, so here Fy is the yield stress of the material, Ag is the gross area of a cross section, gamma M naught is partial safety factor for failure by yielding. Although the steel tension member can sustain a load up to the ultimate load without failure, because once it reaches the ultimate load, then the member undergoes the necking and the failure will happen. Even though it can withstand the ultimate load, because of the elongation of member, at yield itself is nearly 10 to 15%. The structure supported by the member would become unserviceable. Even after the yield stage, the elongation has crossed 10 to 15%. Even at that stage, the structure won't undergo complete failure, but because of that elongation, the structure will become unserviceable. It can't be used for what it has been designed for. Hence, in the design of tension member, yield load is also taken as the limiting load. That is why yielding of a cross section is also considered as one of the failure. Next, design strength due to rupture, break or a fracture of a critical section. If you look at IS 800 2007, again in the class 6.3.1, they have given design strength due to rupture of a critical section for plate. If the tension member is a plate, then design strength is equal to 0.9 ANFU upon gamma M1. Again, gamma M1 is stated in table 5. Gamma M1 is 1.25. Fu is the ultimate tensile stress of the material, and An is the net effective area of the member. We'll discuss separately about the net effective area alone. That itself is a quite. Next, design strength due to rupture of a critical section, single angle. Previously, we have seen design strength due to rupture for a plate. Now it is for a single angle and the other sections. The rupture strength of an angle connected through one leg is affected by a shear lag. So if you look at this picture, it explains about the shear lag concept. An angle connected to the plate. And in the connection, only one leg is connected to the plate. But overall, the whole cross section is responsible to take the load. But at this connection, this angle has to transfer the load to this plate through the connection. So in the connection, all the load which has to be transferred to the plate happens only through one leg. The connected leg is subjected to more load than the outstanding or unconnected leg. Connected leg fails first, then it prolongs to the unconnected leg. Or in other words, the connected member is subjected to more stress than unconnected or outstanding leg in the connection. Or, in other words, unconnected leg, outstanding leg, takes very less load in the connection. Now, this concept is called as a shear lag. Again, load is stress into area, and we have stress into area for connected leg and also stress into area for connected leg. Because of the shear lag concept, unconnected leg takes very less load, and that has been countered in the equation by multiplying with the beta. Beta is the area reduction factor, where beta is given in IS 800 2007, which is 1.4 minus 0.076 multiplied with W by T multiplied with Fy by Fu multiplied with Bs by Lc. Now we'll see all those things in detail when we solve a numerical, where W is the outstanding leg width, T is the thickness, Fy and Fu are the ultimate yield stress and ultimate tensile stress. Bs is the shear lag width, Lc is the length of bolt or weld along the load direction. When loaded, the cross-section area experiences nonlinear bending and shear stress distribution. Due to this, the unconnected leg lag behind the connected leg, as I said earlier. This phenomena of lagging is called as a shear lag. Shear lag occurs when the tension force is not transferred simultaneously to all element of cross section, especially in the connection, in the joint. Research indicates that shear lag can be accounted by using a reduced or effective net area. That is why the beta is coming into picture when you are calculating the strength of unconnected leg. The area that is effective in resisting tension member may be less than the full calculated area. Angles are extensively used as a tension member in truss and bracings. See, here is the example of a truss. See, mostly in most places, the truss is made of angles. So, angles are extensively used. If you look at the connection, one leg is connected to the gusset plate. In all the joint, the angle has to be connected to the gusset plate. And only one leg is connected mostly, and other leg is unconnected leg. So if you have connection like this, then the shear lag comes into the picture. Angles, if axially loaded through centroid, could be designed as a case of plate. However, usually angles are connected to gusset plate by bolting or welding only one of the two legs. This leads to eccentric tension in the member, causing non-uniform distribution of stress over the cross section. So, there exists a shear lag at the end connections. The effect of shear lag and the strength reduction is higher when the ratio of area of outstanding leg to the total cross section increases. Even double angle or connected on opposite side of the gusset plate experience the effect of shear lag. And if the unconnected or outstanding leg area is more from the percentage from the total area, then you will get increase in the shear lag effect. Because we know that this leg takes very less load in connection. If you have more area of the member which takes very less load, then you will get a higher shear lag effect. So the overall cross section area is much lesser than the cross section area of the member has. So the shear lag effect is more if the outstanding member area is more. And even if you connect two leg, even if you connect two angle back to back or on either side of the gusset plate or on the same side of the gusset plate, still you have a member which is unconnected on both the sides. So that is why the shear lag effect will prevail even in the double angle connection. Of design strength due to rupture for a single angle. ANC is the net effective area of connected leg, and AGO is the gross area of unconnected leg. Why we use net? Because in connected leg we put hole. So you have to always consider only the net area of connected leg, and there is no hole in the unconnected leg. So outstanding legs gross area is AGO. To calculate this two area, we use this simple equation. Again, we'll look detail about this equation in the net effective area session. The ANC is a net area of connected leg. AGO is the gross area of unconnected leg. Block shear failure. Member tears away from the connection. There is a combination of tension and shear on failure path. Like tension rupture, there is a more than one failure pattern or path. As we discussed in the failure, the block shear failure may happen like this or even like this. And if you look at this picture closely, this is subjected to pure tension because load is applied in this direction, and this cross section is subjected to shear. For a bolted connection, the design block shear strength TDB is this, which is also given in IS 800 2007. Whichever is less among these two equations, whichever is less, that is the design block shear strength, where AVG, AVN is the minimum gross and net area in shear, and ATG, ATN is the minimum gross and net area in tension. We'll see that in detail when we solve a numerical. Thank you.